Okay, let's get started. Hello everyone. Well, so what did we do last week? Yeah, yeah, yeah. We started doing neural network, right? Like so, which is basically this idea of also learning the representations, like instead of just doing classifications, right? Like so. So before that, we looked. Too loud. So before that, we looked at a bunch of machine learning algorithms, like where typically like these are linear models with some sort of nonlinear basis functions added for the flexibility of developing nonlinear models, right? Like so, now the big challenge with using nonlinear basis functions is that it's not clear how to construct them, right? Like so, if you're lucky, you're going to construct reasonable nonlinear basis functions, like which will make the problem linearly separable, and your linear classifier, like logistic regression or SVM, could solve the problem, right? Like so, however, if your nonlinear basis functions are not good enough, or in other words, like if they don't put the data in a space where things are not linearly separable, then your classifier is going to have a bad performance, right? So which is where this idea of neural networks are interesting, because in neural networks, like so you are taking the original data and you are first learning a projection with the projection layer or the hidden layer, right? Then you're passing this projected data to the classifier. So the benefit is you're learning these features in a completely data-driven way. It's automated. Like you don't need to worry about what nonlinear basis functions to pick. Like so often you would worry about what activation functions to use, right? Like so you could use a sigmoid or tanh or relu. There are tens of activation functions that exist right now. Like so you could pick whatever most recent activation functions are, like, and then like it's typically a linear projection followed by some nonlinear activation function and then the classifier, right? And we discussed how even a single hidden layer neural network could act as a universal function approximator. However, in practice, it's not easy to solve complex problems with the single hidden layer neural network. Like you would require exponential number of units. So we started discussing this idea of deep neural networks, right? So any neural network which has more than one hidden layer is a deep neural network, right? Like, and can someone tell me the benefit of having deeper layers? So like what's the benefit of having two hidden layers or three hidden layers versus one hidden layer? Yeah. So you're doing more transformations, right? Like so now it's important that the activation functions are not linear, right? Like so if you have linear activation functions and you're doing more transformations, then even if you do 5 transformation, it's kind of equivalent to a single linear transformation, right? Like when you cascade linear projections, it's still one linear projection in the end, right? So it is really important that you have some nonlinear activation functions in between. So then it becomes sequence of nonlinear projections. Now, the sequence of nonlinear projections is extremely powerful in the sense like so like it's not a linear cascade, okay? It's a nonlinear cascade. So what happens is after 2 or 3 levels of nonlinear projections, you get a highly nonlinear space. Like that depth often gives you this flexibility of really complex projections that you don't need too many neurons. Like so, like with a reasonable number of neurons, as you increase the depth, you're going to get very high nonlinear projection. Like and hopefully the data is well separated in the space, right? However, training such networks are hard, right? Like so, which is what we were discussing towards the end, right? Like so, we talked about the idea of vanishing gradient problem, like where as you increase more hidden layers, and when the gradient passes through these hidden layers, right? So they vanish or they shrink. So the most important part of the gradient computation was dou h2 by dou h1, right? Like so when you compute dou h2 by dou h1, you get something like sigma dash times w2, where W2 is already a small number because this is the weight that you're initializing close to 0. And for sigma dash, we saw that the range of sigma dash is between 0 to 0.25, which means if you have 4 layers, right, then for each like dou h by dou h, right, like, so you're shrinking your gradient by 1/4. This is at best. Okay, so you would shrink it even more than 1/4. Okay, so every time you're shrinking by 1/4, and this is multiplicative, right? Like, so when you do this 3 times, when you have 3 layers, you're shrinking your gradient by 1 by 4 power 3. So that's going to be almost close to 0. So which means your first layer is not getting any gradients. So it's just staying close to the random initialization, right? So which is why when you train a 4-layer network without any precautions, it's going to work worse when compared to a single-layer neural network. Is that clear? So the whole field of deep learning is about how to fix this issue, right? Like, so we started looking at some solutions. The first solution we looked at was the idea of basically changing the activation function. Like, so what the main culprit here is really the activation function, because if you use sigmoid or tanh, they are shrinking the gradient, right? So can we come up with activation functions which doesn't shrink the gradients, right? Like, so one example is ReLU, which is given by max of 0, x, where can someone tell me what would be the gradient of this f of x? So what's the gradient of ReLU function? So 1 or 0. So it's going to be 1 whenever you're on the positive side, which means you're not shrinking any gradient. You're just passing the gradient. And it's going to be 0 when things are negative. Okay. So because it is just passing the gradient as such, things could compound and gradients could explode, which is the opposite of vanishing gradient. So to avoid exploding gradient, like, you could either do L2 regularization or you could just clip the gradient, right? So again, can someone tell me why clipping the gradient is a good idea? So are we losing anything by clipping the gradients? What are the implications of clipping gradients? So you understand what is gradient clipping, right? Like, so if your gradient is greater than 1, you clip it to 1. If it is less than -1, you'll clip it to -1. Yeah. Yeah, so when you do gradient descent, it's actually the direction that is important than the value, right? Like, so because whatever the value is, we set a very small learning rate and we want to take a tiny step in the direction, right? So the direction matters more than magnitude for gradient descent. So it's kind of okay if you're clipping, because anyways, what we care is taking a tiny step in the right direction. Is that clear? And we discussed how ReLU could have dead neurons. So one solution was leaky ReLU, right? Like, so, but then there are many, many versions of ReLU that exist out there. Like, so we are not going to talk about that here. The second solution we looked at was this idea of greedy layer-wise pre-training, which was historically the first solution that was discovered for training deep networks, like, so, which was based on this idea of autoencoder, right? Like, I'm not going to get into the details of how greedy layer-wise training works, but the basic idea is you train one autoencoder, then you throw away the decoder, you repeat this process so that you have some really good initialization. Then you do the complete training, which is called fine-tuning, right? And we also discussed how this is not solving the vanishing gradient problem. It is just bypassing the problem by having good initialization, okay? Which is why this is not very common right now. Like, nobody does greedy layer-wise pre-training. Is that clear? Any questions so far? So we're going to see a few more solutions for solving the vanishing gradient problem today. Before that, are there any questions? Okay, let's continue. So the third solution I want to talk about is the idea of skip connections, okay, or residual connections. Okay, so let's say I have a neural network which has 4 hidden layers. something like this, right? So we know that gradients vanish because you need to pass the gradient from H4 to H3 to H2 to H1, right? Now, one way to reduce this vanishing gradient effect is to actually introduce some sort of skip connection between the layers so that the gradients can directly pass to the previous layer by skipping a connection. Okay, so for example, like I could have like a skipping like this. Okay, so what does this mean in terms of implementation? This just means that H2 is not just a function of H1, it's also a function of X directly. Is that clear? So now the benefit is if I want to go from Y to X, so previously it took 1, 2, 3, 4, 5 steps, right? So now the gradient can go from Y to H3 to H1 and X. So the number of steps in between X and Y has reduced, right? Like, that is true for like other layers as well. Like, so this kind of looks like a small reduction with 4 layers, but when you train a 100-layer neural network or a 150-layer neural network, like, so for example, ResNets are one of the common like neural network architecture, which is based on this idea of residual connections. Okay, so like you add these residual or skip connections, like, and you're essentially reducing the effect of vanishing gradient. Is that clear? Any question? By the way, some of these solutions that you're talking about are almost all of them are complementary in the sense I can have both residual connections and ReLU, right? So like having ReLU is already helping us with vanishing gradient problem, and I could further add residual connection, right? Like, so the deeper the networks, like you need to have more tricks. Like, so if you want to train a 1,000-layer neural network, which is not very uncommon now, by the way, so people do train 1,000-layer neural networks like easily, which was not at all the case 10 years back. Okay, so if you want to train a 1,000-layer neural network, then you need to have all these solutions added. We're going to see a few more solutions. Like you need to put together all these solutions so that they all together reduce the effect of vanishing gradient, and you can better train the model. Is that clear? Any questions about skip connections? Okay, so the next solution is the idea of normalization. Okay, but as an example, I'm going to use batch normalization, which was historically the first normalization technique that was introduced. But then there are, again, 10 to 20 different normalization techniques that exist out there, like which you can read about by yourself. So batch normalization was introduced by Yoff and Shegedi in 2014. Okay, so here is the idea of batch normalization. So let's take sigmoid and tanh activation functions, right? Like, so they look like this, right? Now, when we say gradients vanish, what does it mean? Like, so it means that your sigma dash is close to 0, right? So when your sigma dash is close, the best value for sigma dash is 1.1/4. And the worst possible value is 0, right? It's between 0 to 0.25, right? So when would sigma dash become close to 0? Yeah. At the top or at the bottom. Okay, so when your sigma is close to 0 or 1, the gradient gets close to 0. Okay, so in some sense, we would say that this activation function has saturated if it is close to this region or this region. Is that clear? Same is true for tanh as well. So the tanh dash is between 0 to 1, and it's going to be close to 0 when your activation function is saturated, when it is close to +1 or close to -1. Is that clear? Any question? So the idea of batch normalization was really simple. Like, so can we control the layers in such a way that they never go close to saturation, right? Like, so in some sense, if I can normalize the pre-activation functions in such a way that they always lie in this region, right? So then I'm going to get better gradients. Now, this is true for any activation function. Like, so for any activation function, instead of going to the extremes, if I can stay in the good region of the activation function, then I should be able to get better gradients, right? Yeah.
But does this work with Rolu? Because with Rolu, it's like uh,
It would still work with ReLU, like so, because the idea here is really to bring it to an intermediate range, right? Like, so it's still going to work with ReLU, and it is also going to help with the exploding gradient, because you're normalizing things, it reduces the chances of exploding gradients in ReLU. Is that clear? So this is the idea of batch normalization. So basically, you take the pre-activation before you apply activation function, like you do normalization. So then you do the pre-activation. Sorry, do the activation. Is that clear? So let's see how to implement batch normalization. So the input for batch normalization layer is the pre-activation. Let's just call it X, okay, over a mini batch of data. Okay, so which is to, let's just say I have a mini batch of m examples. Okay, I'm going to take a mini batch of data and I'm going to compute the mean pre-activation over the mini batch, which is basically 1 over m summation I is equal to 1 to m xi. Okay, so this is my mini batch mean. Okay, then I'm also going to compute the variance. So sigma b square is 1 over m summation I is equal to 1 to capital M xi minus mu b the whole square. So this is my mini batch variance. Okay, so then I'm going to compute new xi hat, which is basically xi minus mu b divided by sigma b square root of sigma b square, and I'm putting a very small epsilon, which is typically 0.01 or 0.001, like that, right? Like, so just to make sure I'm not dividing by 0. Is that clear? Yeah. You could. This is all linear. Like, this is all differentiable. Why? Hmm. Hmm. Well, most probably not, right? Like, so this part is linear. This is the only nonlinear part. Like, so the gradients would still flow. Like, it's not going to shrink the gradients. Okay. Okay. So now here is the extra step in batch norm. So sometimes this kind of normalization is going to hurt the expressive nature of the model. Okay, because you're kind of restricting to a small range, right? What if the actual problem requires bigger range, right? So what they did in batch norm is to compute yi, which is basically some gamma xi hat plus beta. Xi hat plus beta, which is basically to scale and reshift. scalar shift. Okay, so gamma and beta are learnable parameters. Okay, so these are the parameters of the batch norm layer. Okay, so you're learning these through gradient descent, and the idea here is if the problem really requires a different range, then gradient descent will learn those gamma and beta and kind of reverse the normalization that is happening. Okay, yeah.
For the classification problem before 0, 1.
No, this is still pre-activation. So Y is still pre-activation. Okay, so this is not the final layer. So this, the final result of this is still a pre-activation. So then you apply your sigmoid or tan H or ReLU, whatever you want to do. Is it clear? Now, typically this is how your hidden layer is going to look like now. So previously your hidden layer was basically a linear projection like WH plus B, right? Followed by, let's say, a sigmoid activation, right? So this was my one hidden layer block, right? So you have a linear projection followed by sigmoid, or linear projection followed by tan H, or linear projection followed by ReLU, right? This was the hidden layer before. So now with the idea of batch normalization, the hidden layer is going to look something like this. You have a linear projection, let's say WH plus B. Then you have a batch norm layer, right? Then you have your sigmoid activation. So this is going to be my one hidden layer block. Is that clear? Of course, if you want to implement this manually, you need to compute the gradient for batch norm layer and implement things by yourself. But if you're using things like PyTorch or TensorFlow, like or JAX, they're going to do the automatic differentiation for you. So you can be crazy about the kind of normalizations that you do, as long as it is differentiable, the gradients are taken care of, right? So which is why people have developed a variety of normalization techniques. Like some of the most popular ones are layer normalization and RMS normalization. Okay, so I'm not going to explain what they are, like, but you can read about them. They're just different ways of normalizing. Is that clear? Any question? Yeah. Well, you'll typically initialize gamma and beta to some small value and just learn them like how you're learning the weights of the network, right? Any other questions? Yeah. YI is? No, it's no. So this is YI is just the pre-activation. So then you have the activation, then you have the output of the layer. Okay. So pre-activation is anything that goes to the normalization layer, right? Like typically you will have WH plus B. So this is going to be the output of the layer, right? So this is what I mean by pre-activation, anything that goes inside the sigma. So instead of this, with normalization, it's going to look like Y is equal to sigma of batch normalization of WH plus B. So you will do this, then you will do normalization. That is the pre-activation for sigma. Is that clear? Any question? Okay, so if you look at the most modern deep learning architectures, you would see that they almost always use some sort of normalization, some sort of skip connection, right? Like some modern activation function, etc. So like every solution that we have learned, like you need to put together all of them, like if you want to train a state-of-the-art neural network. Is that clear? Any question? Okay, so now this is all modifications at the architecture level, right? Like so changing activation function or adding skip connection or adding this normalization layer, right? These are all changes to the architecture so that we can train bigger and deeper models, right? Now, we also need to work on our optimization methods, like if you want to train deeper models, okay? So far in this course, like we have been using vanilla gradient descent, like some form of vanilla gradient descent, right? Like so we did stochastic gradient descent, mini batch gradient descent, or a full batch gradient descent, right? Like so, can someone explain the difference between these three variants of gradient descent? Yeah.
I think you computed one point at a time.
Yeah.
Not computer using all the points and mini batches, you know.
Something in between, right? Like with mini batch gradient descent, like you pick a batch size, like 100, 200, 64, whatever, and you will compute the gradient just for the batch, right? So we have looked at these three different ways of doing gradient descent, but it was still simple, like standard gradient descent, right? Like so, for the rest of this lecture, like we're going to look at various ways in which we could improve this gradient descent algorithm. Okay, so we're going to revisit optimization. Okay, and just as a recap, let's say we have some data set of a bunch of xi yi for I is equal to 1 to t, right? So we have seen batch gradient descent, which is basically theta is equal to theta minus alpha times the gradient of the loss function, right? With respect to the entire data set. So it's x1 to t, y1 to t, right? So this was my batch gradient descent. Like, so I'm computing the gradient of the loss function or objective function j with respect to all the examples, like all the t examples, right? So then we looked at stochastic gradient descent. The idea of stochastic gradient descent is theta is equal to theta minus alpha times, okay, the gradient, but the gradient was computed with just one example, some example xi, yi, right? So we pick one example, compute the gradient, update the parameter, and continue this forever, right? So then we had mini batch gradient descent. The idea of mini batch gradient descent was theta is equal to theta minus alpha times the gradient, right? For a small batch of examples like xi to I plus n and yi to I plus n, where n is much lesser than t. Is that clear? Now, one thing to remember is when you do full batch gradient descent, you will have some sort of monotonic decrease in loss, right? Well, that's because gradient descent typically tries to find the closest minimum, right? Like, so if you have a loss function which looks something like this, and you're here, and you're doing full batch gradient descent, which means every time step you're getting the true gradient. So you'll take steps in such a way that you reach this region, right? However, when you do stochastic gradient descent or mini batch gradient descent, so the gradient that you're getting is just a stochastic approximation of the true gradient. So which means this approximation is going to have some errors. So sometimes you will move in the right direction. Sometimes you will move slightly differently, right? But this is still an unbiased estimate in the sense, on an average, you're moving in the right direction. But individual steps might not be always in the right direction. Like, so you can move like this, like this, like this, like this, like this. So basically, like you're taking steps, you're decreasing the loss on an average, but like you might go up, come down, go up, come down, like simply because this is an approximation, right? So this is why typically when you train a neural network with stochastic gradient descent, like so your loss would look something like this. Like, so it's not going to be like a monotonic decreasing loss function. Like you're going to see some spikes, like so the individual loss might go up, come down, go up, come down, right? Like so simply because of the stochastic approximation, which could have some errors. Is that clear? Any question? Okay, so now we're going to talk about different ways to improve the stochastic gradient descent algorithm or gradient descent in general, okay? Now, there are a couple of main challenges that we should address, okay? So first one, which is basically the most important question in training machine learning models is like, how do you find the optimal learning rate, right? Like, as I said before, learning rate for gradient descent, the step size, is probably the most sensitive hyperparameter or the most important hyperparameter in machine learning, okay? Any project that you're working on, like you have to tune your learning rate. Like, so it would look like your method is not working at all if you have a wrong learning rate. Just changing the learning rate could make a huge difference in the training, right? So basically, the first challenge is how to tune your learning rate. Okay. The second challenge is if you read the most recent machine learning papers, like so you would see people not just using one learning rate, but they would use what is called a learning rate schedule. Okay. Now, depending on which part of the loss surface you're in, for example, if you're far from minima, you could take larger steps. When you're closer to the minima, when you're doing mini-batch gradient descent, it's noisy, so you want to be careful, so you want to take very small steps, right? So this is what people call as learning rate schedule. Okay, so you would see that, let's say your loss is decreasing like this. Every time you reduce your learning rate, you will see a drop in the loss like this. Okay, so this is a significant drop because if you continued with the same learning rate, you're going to converge like this, right? But just changing the learning rate here made another progress. Changing the learning rate here made another progress. This is used almost in every recent paper that you can read. Okay, so all the new models that people develop, they have some sort of learning rate schedule. So then the question is, how do we come up with this learning rate schedule? Like you would see papers saying, oh, for the first 10 epochs, we used learning rate of 0.01, then we reduce it by half for the next 10 epoch, then we reduce it by half for the next 10 epoch, right? Like so there are other ways of doing this. Like, for example, people would start from 0.1 and have a linear decay all the way up to 0.01 for every step, right? So there are many ways in which you could do these learning rate schedules. Okay, so the question is, how do we come up with a better learning rate schedule, right? So then the third issue is the way in which gradient descent works is there is one step size, and you're using the same step size for all the parameters, right? Like, so we are basically having one learning rate for all parameters. Is this a good idea? Let's take a 10-layer neural network. Okay, Is it a good idea to use the same learning rate for all the 10 layer parameters? Okay, can someone else tell me why it's a no? So why is it not a good idea to have same learning rate for weights of all the 10 layers of neural network? What is a better strategy? Like if I want to come up with a heuristic for choosing learning rates, right? Like how should I choose the learning rate for the first layer, second layer, third layer, all the way to 10 layers? Yeah. Okay. Um, okay, but can you give a general heuristic independent of activation? Yeah.
It feels like gardening, like the first layers will impact a lot more of than the last layers, like because it propagates. So I would have like a smaller learning rate at the beginning.
Okay, is that a good idea to have a smaller learning rate in the bottom? Yeah.
Instead of every layer parameter, like we check for every layer. If a small change in X causes a big change in H of X, then we tune the learning rate to be small.
Okay, now you're all thinking about more complex solution. Like I'm looking for the simplest solution that we could do. Like so, okay, maybe I'll rephrase my question. How should I set the relative learning rates for all these 10 layers? Yeah.
The data set is in balance. Like if there are more of certain things that are curing than others.
Okay, well, that's a different problem. So I have 10 layers. I'm doing gradient descent with these 10 layers, right? Now think about the vanishing gradient problem. Like, so if I have to solve vanishing gradient problem, should the bottom layers or the initial layers have higher learning rates or smaller learning rates? Yeah. Should have higher learning rates, right? Like so typically if I have a 10 layer neural network, ideally I should be increasing the learning rate as I go down the depth. That's one way to solve the vanishing gradient problem, because vanishing gradient problem means that like the gradients are getting smaller. I can compensate for that if I have a very high learning rate, like 10 times higher learning rate than what the learning rate of the first network is, right? So this is the simplest possible heuristic. So your heuristic is bad because if you have a very small learning rate, you already have vanishing gradient problem, right? Like you're just making it worse, right? So what did you say? Okay, so that's actually a good idea. Like so you could look at the sensitivity and adapt the learning rate accordingly, right? Like so it's a bit more complex process. As you can imagine, you can invent new ways to do this, right? Like so this is what a lot of optimization research nowadays is. Like so people are trying to come up with new heuristics or like new, more principled algorithms for changing the learning rate at individual layers. Okay, this is an important thing to consider if you want to train very deep neural networks. Yeah. Well, that's what we're doing now. So this is another way to solve vanishing gradient problem. Okay, so if you have a properly tuned learning rate, you can train a 10-layer sigmoidal neural network without vanishing gradient problem. Okay, a really simple heuristic is just keep increasing the learning rate for every layer. So this is going to compensate for the vanishing gradient problem. Yeah.
I would say, well, mine is like if the learning rate is higher, you risk getting closer to the limit.
No, well, so the gradient is too small, right? Again, remember when you take steps in gradient descent, the magnitude doesn't matter. Like what matters is the direction, right? Even though the gradient is too small, it still has the true direction that you want to move on, right? So we are just increasing the step size instead of decreasing so that we can make progress. Is that clear? Any question? Okay, so we will talk about how to address all these different questions. Okay, so in general, like what we're going to do for the rest of this session is to develop new optimization methods. okay, that are better than gradient descent. Okay, let's just call all these methods as gradient descent plus plus, right? Now, specifically, we're going to look at two different ways to improve gradient descent, okay? So first is through the idea of momentum, okay? Then second is, oh, just 1 second. Okay, I think my laptop might have died. Okay, it's going to take a few minutes. So let's just take the 10-minute break now. So then we will start with new gradient descent algorithms.